Ready? They're gonna go live. So I should actually not tell you when you're live, so that the beginning looks kind of random. What do you think?
Fun and
Yeah.
yeah, it's already fun. Already
Yeah,
fun and random.
we've been live for about a minute now. So
Wow.
yeah, I mean, this is how we indicate that this is an actually random conversation.
Say something bad about the
and-
audience.
Okay. Hi, everybody. As you saw, we are all ready for the session. I hope you're excited to hear about AlphaCode. Today, I'm with Ehsan, Suhas, and Serena. You probably have seen all of them in previous videos. But we are going to talk about AlphaCode, some interesting results that came out of Deepmind recently. And to get us started, I'm going to ask Serena, well, after she takes a sip, to tell us what the whole thing about AlphaCode is.
I thought we were going to get started by all sharing what we're drinking. Can we do that quickly? I am drinking some black tea in my Bodum French press. Suhas, what are you drinking?
I'm imagining drinking a Diet Coke.
A Diet Coke, you said?
Yeah, I'm imagining it.
Yeah, okay.
Yeah.
That's a good imagination.
I'm the
Ehsan, how about you?
I imagine drinking coffee, but I had a chance to get just water. So water for now.
Very healthy.
Okay. Very healthy.
What about
I'm
you?
drinking black tea and thyme.
Black tea and
It's
thyme?
a home blend. Yeah, it's a home blend.
Oh, nice. Mine's black tea and
I started
cardamom.
Oh, interesting. Yeah. I just had these two at home and just mixed them and made them tea.
Nice.
So.
Should start a tea business. I buy Aggregate Intellect.
Exactly.
Yeah. Okay, great.
Right.
Now that we've done the intros, we can get started.
Yes.
All right. So on February 2nd, yesterday was February 22nd. Today is the 23rd, I believe. So on February 2nd, 2022, this year, Deepmind published a blog post titled Competitive Programming with AlphaCode, I believe. So essentially, AlphaCode is this program that writes code at a competitive level. So in experiments or competition, AlphaCode placed at the level of a median competitor, so like 54th percentile, I believe. I would say it would do better than me in these coding competitions. And it's apparently the first time that an AI code generation system has reached a competitive level in these coding competitions. And taking a look at the AlphaCode paper, this is also the first time that such a system has been able to go beyond just translating instructions into code. So very exciting stuff. Yeah, and essentially AlphaCode is this code generation program. So given a problem statement, AlphaCode can read the whole statement and produce code similar to how a human like any of us would do. And if you look at the examples on Deepmind's site, in the article about AlphaCode, this blog post that they published on February 2nd, it's really interesting to see the code. And I even noticed the use of like the pop function in Python. And I think that's actually pretty impressive that AlphaCode was able to use functions like this. And just looking again at the article, the founder of Code Forces, which I think is a coding platform or competition platform, someone named Mike Mizayanov, says that AlphaCode exceeded his expectations. And I feel like Mike, in a sense, speaks for many of us when we say that it's very surprising that some sort of AI system can code at this level. So I thought it would be great for us to talk about what AlphaCode actually uses. It's not a surprise that the system uses our favorite architecture, the transformer. And I was going through and would love to hear from everybody else what they feel the novel contribution is of AlphaCode. It seems like there's sort of three main contributions. So there is a large-scale data set, there's the large-scale transformer architecture itself, and then there's also large-scale and efficient sampling that is applied. And the authors say that these three components are like contribute to the main or key success of AlphaCode.
So I'm going to jump in and make sure I understand what's happening because I didn't get a chance to look at the example. So based on what I read, they picked a bunch of competitions that had more than 5,000 participants previously and tried to reproduce essentially tried to do the competition and then see where they rank against whoever participated in those competitions. I mean, anybody can jump in.
Yes, yes, that's what they did, and I think their top performance. Uh, yeah, I think they for one of the competitions they got in the top 54%, where there were like more than 5,000 users there, and I think for many of these competitions, you can say that it's a pretty impressive task because there are literally like a lot of top programmers that are participating in these specific competitive programming challenges. So it's not an easy task, definitely.
So it's not just people who are like practicing for interviews. It's like AlphaCode went up against people who truly do this for fun, but are also very good at it.
Yes.
I'd be curious about the ratio of that because one of the Reddit threads that I was reading about this brought up that point that who's actually participating in these competitions and is being in the top 50% or barely in the top 50% actually impressive. So and I assume the number of people who are actually competitive is going to be a smaller portion versus the larger population that is probably job seekers who are just practicing coding. But can you put that in context? Like, is it actually impressive from your point of view?
So I think there are
Especially since you saw the examples.
I think there are two different modes of comparison. So you can compare it against models in the past and see how this model compares with respect to those models, or you can compare it against actual humans. The human to computer comparison is not apt, and it's not comparable directly on for many different reasons. Um, yeah, so from a perspective of just comparing it against previous models, I would say this is like a very significant achievement. But when you compare it to humans, I guess the jury's out on this one. I'm personally still skeptical. I'm not, an AGI champion, or I'm not advocating in that direction at all. So I don't think humans will see the benefits of what technology has been developed here for quite a long time to come. Um, but it's still an impressive achievement, just like Deep Blue beating Kasparov was an impressive achievement, and IBM winning Jeopardy was an impressive achievement. It's also a very significant engineering challenge.
Yeah, and I'm
I saw it again.
wondering.
Sorry.
Yes, I'm wondering. So, what is the? And I think I asked this a bit when I was talking at first. So, what is the main contribution? What is the engineering feat? The engineering feat is being able to train such large models, and is that not a way of Deepmind? Like, is Deepmind, are they boasting their engineering capabilities or sort of their compute cost capabilities?
Yeah, I think there is a lot of engineering wizardry that needs to be performed in order to scale this to this level of parameters. Doing anything above like 5 billion parameters needs like massive parallelism and all kinds of engineering exploits. On the other hand, there is also, I guess, a lot of decisions to be made with respect to data filtering, because you need to have like really um, you know remove all the noise in the data, and you also need to have some very specific parameters for the transformer architectures and so on. I think as an I guess you agree that it's both about engineering skills and also some very well informed by a whole lot of experiments, like deep learning architectures. Yeah.
Yeah, agreed. I want to emphasize, it used to be the case that one could just pick up a laptop, possibly a power station, and do these things and run experiments and show results. These days, it's becoming less and less. Well, it's actually walking to two very different directions. So one way, it's in one sense, it's becoming less and less accessible, and in another it's becoming more and more accessible. I know it sounds contradicting, but I'm going to mention it quickly, in detail, before then coming back and talking about the parameter size and how it affects the experiment. So on one hand, the sheer growth in parameter size, let's just put it in perspective quickly. So the original transformer architecture started with just millions of parameters. Then it moved on to BERT with around 110 million parameters. Then GPT-2 around 1.5 billion parameters. So we see the growth is actually in orders of magnitude. And then GPT-3 around 175 billion parameters. I think for GPT-4 it's expected to go beyond trillion parameters. And I think as Suhas rightly pointed out, I think AlphaCode is using 4.1 billion parameters. So this many parameters, it's not really feasible to run on a local GPU. However, big of a power station you may have, and becomes more and more expensive. But on the other hand, there are elastic compute available on the cloud, so you possibly can. You don't have to buy the expensive machine, but still running it is expensive, and training it from scratch is expensive. It's going to cost you a lot. So it's become less and less accessible. But the good thing that's happening, especially with attempts such as AlphaCode and other more open companies, is that they're releasing the pre-trained models, which makes them more and more available. So one can just pick them up and tune them to the direction they would like to, and they save on all the compute that they would have required otherwise to train. So now getting back to the point, it is certainly an engineering effort to train these things from scratch and build the original model. Now, from that point on, though, if you're a user, you just want to create a model that tackles a specific type of task very well for your company, you can just pick it up and do it. So in that sense, it's they did the work for us.
So I occasionally look to the side, and the reason is that I'm looking at the YouTube comments. So if you're watching this on YouTube, please write comments about anything we are saying. This is a random conversational exchange, I guess. And if exactly, and if you have any thoughts to add, please write it as a comment on the live chat, and we'll try to address it. We also have collected a lot of resources that we will publish after this session, along with this video, where you can read more about all of the topics we're talking about. So I want to go back to how it works. So I think one of the interesting things that I read is that the code is able to start from natural language instructions and turn those into code. And it produces around 1 million sample, code pieces that can run that task, and then test it against some test criteria, and then there's a bit of a survival mode, like selecting the ones that survive, etc., etc. So yeah, I mean, either Suhas or Ehsan, do you want to walk us through a bit of the technical details of how that's happening? What are some of the considerations on false positive rate and all of the other details for evaluation that is happening?
Mm-hmm.
I can take a quick stop and pass it over to you, Suhas. So, that specifically, is one of their main contributions. In the past, we've seen kind of 2 points. One is, I think Serena alluded to a little bit earlier, is that previously with Codex or previous OpenAI showcases, we went directly from instructions to the code, right? And instructions are very transparent, and accessible to the model. Here you see problems which are a little bit more convoluted. Like they still want you to solve it. I don't think there are too many trick questions there, but it's a step further into intelligence, which is ultimately the goal of Deepmind, right? So that's one. And another one, it seems the way they tackled. So previously, and I'm not sure if there's, I'll be glad to hear your thoughts on this, Suhas, but I'm not sure if it's directly comparable to Codex per se. But if we want to draw a very rough apple versus oranges comparison, with Codex, in the test set that they had, I think they covered around, if I'm not mistaken, around 30% of the instructions were successfully turned into, of programming languages out there were properly turned into code. I think the improvement over there is that they buy this mechanism of generating a lot of samples and then filtering them by ranking and a few other mechanisms that they utilize. They ensure reaching at a high quality solution. So just these 2 points before passing over to Suhas.
Yeah, thanks. So with regards to your comment about Codex, I guess since Codex was not specifically fine-tuned on this dataset, the competitive questions dataset, I think maybe we can't compare it directly because Codex would be more I mean, it was trained for generating shorter snippets rather than the competitive programming questions that AlphaCode has been fine-tuned on, which has like a very specific format. Like most competitive programming questions are of the form like there is a very irrelevant narrative kind of paragraph at the beginning, followed by something more specific that actually contains the meat, and then followed by like test examples, and then an input output format. So being able to fine tune on that particular structure gives like AlphaCode a very big advantage in solving those particular problems. Regarding the how it works, I think there are
Sorry,
some
can I
ways.
ask you
Mhm.
clarification right there? You said they changed the input and output like that. I didn't quite understand that part.
Oh no, I meant there is a very specific input output in the question. You are given an input and output format. So that is also present in the fine tuning training set for AlphaCode. So it understands what exactly the structure of the question is going to be in natural language, which, for example, Codex has not seen because it was not fine tuned on these specific types of programming questions. Yeah. Yeah. So going back to, I guess, the model, I guess some of the key ingredients would be just the pre-training. It was pre-trained on a whole lot of code, 875 gigabytes of quality code. So there has been, so I think data filtering is a very important step. So some of the things that they mentioned that they did was removing files that are over 1 megabyte, trying to remove things like auto-generated code, removing lines that are over 1,000 characters long, removing duplicated sentences or very near duplicates. So it has been shown in several papers that uh, removing duplicated data in your pre-training data helps a lot with respect to performance, also prevents memorization, etc.
And
So this.
Suhas,
Mhm.
so just a question about the pre-training task itself. So there's all these filtering that are or filtering steps that are applied. What is the pre-training task itself? I know that in similar work, so BERT, for example, has 2 different pre-training tasks, like prediction of the next, like a mask token, and prediction of the next sentence. What exactly is the task for AlphaCode?
Yeah. So for the architecture is an encoder decoder model, and the encoder maximum token size is larger than the decoder one, because the programming questions are quite descriptive in this particular competitive space. So for the encoder, they use the masked language modeling, and for decoder, they do use the next token prediction. So yeah, they use very similar pre-training objectives like the ones we do for other language models. The only difference being this is like pre-trained on code, so that means there are also tokenization that is code specific. So they only have like an 8,000 token set of tokens, and you will have special tokens for things that are very, I guess, specific to programming languages, like for example the tab in Python, like the 3-4 spaces. So that would be treated as a single token, and so on. Yeah. So yeah, once you have this,
I think they had a, if I remember correctly, they had a temperature parameter that I mean, it's not novel to them. I think some
yes,
some folks have used it in 2020, 2021, right before the token prediction that is a coefficient. I think right after the logit, that kind of smoothens or sharpens the prediction. I think smoothens it during during training and sorry, I think sharpens it during training and
sharpens it
smoothens
during.
it over during inference. That was the
Exactly.
only kind of that was the stark difference
Mm.
that I saw, as well as compared to kind of older generation models.
Yeah, it was
So
interesting that,
for
yeah.
people who are less familiar like me, what are you talking about? What's the temperature? Is that a sampling related parameter that they're tuning?
Well, here it's just to make sure that your outputs are more consistent. You get better performance during inference, right? And it's a parameter that you can tune. And doing this, so this technique does help, but it's not really established. So actually, the paper says the original paper shows something, and AlphaCode shows the opposite effect, but it does have an effect. It definitely has shown effect. Like for this case, again, if I remember correctly, it sharpens the distribution of the tokens in training set, which results in a smooth prediction and inference. So you don't see, sharp variations. So does
Yes.
that align with your understanding as well?
Yes, yes. And I do remember reading that passage in the paper where they say some other paper actually. So here they use the temperature as something like 0.2, and in another paper they actually used it above 1. So basically, what the temperature would do here is, so you divide your logits, the outputs of your model, by a number, like here in this case 0.2. So what that, and then you put it through a softmax function, and what the end effect of this is that it makes the, because the way the softmax function works, it makes it overly more confident on the top choices. So the lower the temperature value, the more confident it is on the top choices. Imagine if you increase the temperature, if you increase the temperature all the way to infinity, it will be like uniform sampling. So that's the temperature is mostly used to, I guess, determine or specify how confident the output of a model should be like.
So it sounds like the temperature parameter is one of the, I guess, architecture additions to AlphaCode. I also saw in the paper that there is this multi-query attention that they use to reduce sampling costs. And my stab at understanding this is that there's a full set of query heads. The key and value representations are shared across multiple attention blocks, and somehow that, well, I guess there's less parameters to learn, so this reduces memory usage. And first of all, is my understanding correct? And second question would be, is this a sort of architecture that we can expect to see more in the future as the scale of these problems continues to increase? I know Asan has some experience and some thoughts that he might be able to share about like large scale training and what we might expect in the future.
Yeah, I mean, that's a brilliant point. My points, specifically regarding this is kind of how it's changing the landscape after you're offered these massively trained and massive language models, right? Because it basically provides the machine learning researcher with a new set of tools that they can use, and we haven't explored really exhaustively how they can be used. So you can see that the machine learning pipeline is slightly, but and this change is very recent. It's 2020, 2021, 2022 mostly, that it's kind of really becoming a surge, and I expect it to become dominant moving forward. Is that training these language models from scratch is becoming low-level work and a baseline that not everyone probably will do. Excuse me. And now how to utilize that? So as part of your as a tool, part of your tool set, you're given now a massive language model. Now it's now how you can use this tool is going to be something that it will be more and more exhaustively searched or researched on moving forward. And there are three methods that are fairly dominant, and you can, I think, in the material, Amir, on your platform, people can refer to them. I've left a link to that article there. But basically, it started with, there are three transfer learning methods. So all of it, is going to be transfer learning because you have a model to start with. You don't have to start from scratch anymore. And these models are very generic, right? In comparison to what we would have done with expert systems, even with statistical learning in the past. Now, so everything to do is transfer. Everything you're going to do is transfer learning. The original method that people have used mostly, either segregated or joint, is fine tuning. So if it's joint, it's one network. You freeze lower layers or you unfreeze. It's up to you how much you want to remember from the past and how much to learn, and then you train the top layers. Okay, so that's one way. And fine tuning, if you segregate, if you have two networks for any architectural reasons, that's actually very useful to do. They still call it transfer learning sometimes, but sometimes these days they also call it probing. So you use a network, you probe it, you see the output, and evaluate, go back, right? So these two methods, that's one category, and there are three categories total, right? And this other category that kind of GPT-2, GPT-3. I don't remember seeing it before GPT-2, so maybe they initiated it. But it was prompt design, where you give a prompt. So you already have a network. You give it a prompt, and the output, the desired output, with only a few examples, you can achieve few-shot learning. Sometimes even one-shot learning with that pattern, right? So the network is ready to go. It has a lot of advantages, right? So not that much of a training, not that much of a training data either. And then lastly, this new method that has recently come out, I found it very interesting. Again, I think this is from Google's AI lab. You can be very innovative in the way you prompt these networks, and it works. So instead of just giving a text, a string, you actually can give it an embedding that you're learning. So these are learnable parameters in addition to the prompt, to the input of the task you wanted to do. So it's very similar in neuroscience. You have these invasive methods that you obviously don't try this at home, but you inject poles into a monkey's brain or an animal's brain, and then kind of prompt it to do interesting things, right? So it's very similar to that, and even more powerful, because now you can tell the network exactly what you want it to do. So you can explore that entire parameter space, whatever it is, whatever exists in GPT-3, you can explore it with this new pattern, and they call it what do they call it? Model. I think they call it prompt tuning. I'll double check and let you know. I think they call it prompt tuning. but it's very powerful, and this is what what I really expect the research to do more and more. So basically, instead of just prompting or training or fine tuning whatever was used in the past, you provide a massively trained language model with an embedding vector and the input. You can give it the output to train it as well, but basically that embedding will help you even very very kind of delicately um, prompt the language model for an optimally desirable answer or response.
So is that what AlphaCode is using, like the last method that you talked about? Because I remember, I think in our Copilot conversation, we also talked about that briefly, no?
I didn't see that in AlphaCode. So if you saw it, let me know. I think I was more kind of indicating, but this is what you can use.
Right.
If you want to use AlphaCode to generate whatever you want it to, and it wasn't, you don't know if it was trained for it specifically, or at least it wasn't tested for it. You can do that. So that this is gives you more freedom to tackle tasks that the authors of the model didn't even think of, but the knowledge is distilled in the model per se. So that's one point. The other thing, just remember about testing, was also another contribution of code for these competitive programming tasks. They do. I just want to emphasize they do. Publish very nice set of test sets that you can evaluate your generation against. So and that's a benchmark that I had not seen before, at least for competitive programming. So a slight change of topic, but just as exciting.
Very interesting. So I guess since I mentioned Copilot, what are the differences of AlphaCode and Copilot? Maybe Suhas, you can take a stab.
Yeah, I guess it's um, so one is the what it's being fine tuned on. As I mentioned earlier, I think it was just fine tuned. This one was fine tuned on programming, competitive programming questions, so that it can perform in these particular programming challenges. Um, I think there is also certain architectural differences. So the Copilot was based on a decoder only model. So this is an encoder decoder model. So that is one more difference. I think that with respect to the data set, yeah, there are differences in the way that the repositories were chosen, and yeah, so there are differences in that sense as well. But overall, they still use like the standard framework of using a language model, pre-training it, and then yeah, fine-tuning it on specific tasks. So a lot of things remain the same, and that is true as the field converges towards all things transformers. So we have a formula that at least for the next few years is going to be applied to just about every problem that you're going to see. Yeah.
Another thing I'm wondering about the difference between Copilot and AlphaCode. I can't remember if the three of you talked about this when you did the Copilot session. I think Copilot, does it expose PII in any code, and is it the same as AlphaCode? Like, is this a big thing that we're going to have to be as we march towards transformer everything applied to every sort of problem? Is this something we're going to have to worry about?
Yeah. So I remember trying out Copilot, and it looked like there was also an article that I read where it looked like not just certain types of PII, but certain words that are kind of abusive, etc., were blocked from being generated by Codex. I would imagine the same guardrails are applied to AlphaCode as well. But with respect to PII, it's a very hard task. So there was a interesting tweet that I saw just like a couple of days ago, where someone talked about how when Codex was actually generating comments, they generated the GitHub name of a PhD researcher who was working in the same field as the person coding it. And this has very interesting implications. Imagine like this is like an automatic plagiarism creator. So it you can imagine it taking code from various sources and then putting the comments as it's coming from this person, and you know everything here is happening without with coercive consent, as the person who tweeted it mentioned, because you actually check you check the check mark in your terms and conditions in GitHub. But that is, it's kind of like a coercion, because if you don't check it, then you will have to change your entire development pipeline. You have to move out of GitHub and use some, what are you going to use, some primitive system, and go back to the 90s. And yeah, so it's really yeah. Yeah, so the implications there are interesting with respect to copyright, with respect to legality, and so on, and also the fact that these tools are not going to be free. So that means, like, for example, if you are in an interview, uh, right now when I am interviewing candidates, I tell them Google to your heart's content. But imagine some of the candidates actually can pay money to hire, to use some of these tools that can. It's not going to make much of a difference today, I guess. From my personal experience, Codex harms you more than it helps. In terms of your capacity for learning new things, etc. So, but in future, you could think about these issues as being hindrances to to a more fairer society.
What are some of the other examples of PII that could exist in code other than the GitHub names of people?
So you can think about AWS secrets, so passwords being stored in plain text.
Right.
So, like, I know that there are some people who would say that is not good security hygiene, but you shouldn't expect people to be, yeah. So those are some of the other kinds of PII that you can find very easily in, but it's also the kind of PII that is, I think, more easily detectable and thus easily anonymized or remediated.
Yeah. I mean, the fact that one can imagine you can have a prompt pattern and try it by all means, just to tackle that, right? To filter them out. So the fact that it has the understanding to generate those and sees the correlations can be used to also privatize them. So I think that can be done. I don't think that's, to be honest, too far away, as Codex already did to a good extent, right? And I just do want to say that with any technology, this seems unfortunately the case. It can be used for nefarious purposes and really good purposes. So I want to say that I think this technology will enable us to do just a ton more, even to preserve privacy of folks. Just one example was what I just spoke of. And maybe linking it also to what I mentioned earlier with the new kind of prompt tuning pattern. One can, I wonder if one can use the embeddings to generate the code, but not any private information, that goes with it. So that's kind of an interesting area also to explore. Just you can have perhaps a private embedding that when passed and will learn and pass to the network. And perhaps I'm saying because it's very experimental, basically just an idea. You can pass it to the network and ask it to be more private, right? without any pre-training or post-training. Well, technically a little bit of post-training, but yeah, that's another interesting thought.
Yeah, we have a question from the audience actually, which is very exciting. Ian asked something, and I think both or everybody has sort of touched on this, but I'll ask it again just to be sure. So Ian asks, given what we've learned through AlphaCode, are there new doors or avenues of research that are opening up? And I think specifically, maybe we can think of domains as opposed to competitive programming. No ideas. That's okay. So we're stuck with competitive programming.
I can take a quick stab at it, but we, as you mentioned, we kind of indicated a little bit that these can would more and more be used to apply to new domains, even domains that the authors didn't originally even think of, right? So so the for example, right now it's competitive programming, but one obvious domain is actually having a business case coming in and just have the machine write the code. Of course, it's not flawless. Some of them Suhas and I just discussed a few minutes ago, some of the flaws. But imagine a programmer's job will be facilitated from writing the code from scratch and figuring out all the flaws of logic that usually happens and spend a ton of time debugging, to just reviewing a code. So it's like, it's your low-level programmer and you just pair program. I think that's one of the angles that they advertise it. You just pair program with the machine, which is much faster. It's even faster when, like, it's faster than you are in typing, right? So I mean, given you have a good compute to run it presently, there is going to be a little bit tangential, but there is going to be much of the future work in kind of quantizing and making these models more compact, so that they can be run even on edge devices. That was the case with deep learning when it came out at first. Everybody was saying that, okay, you get a good performance, but where should I run it? Earlier experiments show that you can just quantize it to to basically zeros and ones, getting rid of a lot of knowledge, I would say, within the representation, but still perform really well in real world setting and applications. So that's another kind of domain that will rise.
Mm-hmm. So
Speaking of
yeah,
sorry, I just wanted to go on.
Yeah, I was just talking about other tasks in the ML for source code space that are also being actively researched on, and that would benefit from the existence of large pre-trained models trained on source code. So for example, some of them being code to code translation, converting from one language to another, would be very significantly useful in companies where they have dinosaur code bases from the 1970s, and if they want to switch to something more modern. And then there are a whole host of other tasks that we actually discussed in a previous video at Aggregate Intellect itself. And I think it would be interesting to see that. So we at Aggregate Intellect, we are actually have a research group where we were working on code-to-code translation using Facebook's transcoder model, and it was actually showing pretty good performance for Python to C++ conversion.
And for anybody who wants to join that competition, there will be a link to our Slack workspace in the show description, in the YouTube video description. Just click on it, join the workspace, and message Suhas. Speaking of machines being faster than us, though, one of the interesting topics I saw on Reddit that people were talking about was how much of what we are seeing in the case of AlphaCode is essentially machine figuring out inefficiencies in our processes versus actually being able to reason. The implication being that if it were able to reason, it can generalize better versus trying to just finding human inefficiencies and overcompensating them. And one of the examples that the person gave on that thread was the IBM's machine that did Jeopardy. Like there was this big question, like how much of it was actually the machine being able to hit the buzzer faster versus actually coming up with good answers, right? So there's there is that question of is it actually able to do reasoning now, or is it performing better than the other 50% of people who are not very good at operationally laying out their code? So that was a very interesting topic that I hadn't thought about until I read that comment. So I'm curious to hear your thoughts on that.
I have one thought because you mentioned Watson. So one is that task, Jeopardy, is much constrained than the tasks that we have at hand. From the creative aspects, from reasoning, from the kind of the understanding of analogy required to generate code. Right, it's just much more limited. Watson's, I think the first kind of iterations were, it is technically an information retrieval system, just a search engine, right? And it downloaded back in the day. I think it was argued that it was not connected to the internet, but technically the entire internet at the time was downloaded in their kind of supercomputer. So it had access previously indexed, and it would just retrieve the information, right? So information retrieval is a great area in AI, and it's actually much more advanced than it was back then nowadays, but still very limited in reasoning. Now with the argument, we're kind of as humans constrained by the chemical reactions in our brain, and they are slower. Than even if I have retrieved the answer, it takes longer to press the button. So that's a fair argument, and I didn't look at this. It just wasn't interesting enough for me to take a deep look at it to see if that was the case or not. But from what we're seeing here, I think there's a lot of creativity learned with these transformer architectures. Things that you are not exposed. So what is creativity? It's something that you're not explicitly teaching a machine, but the machine can analogously kind of infer. And that's the case. It's been shown a ton. But so there are a lot of novel sentences being generated that was just beyond. Even 10 years ago, beyond the power of the machine learning tool set in general. The best thing we have these tools to evaluate them, such as Perplexity, and it just sounded like a very random rambling, like it didn't really have any coherence. So there was a lot of anyhow. So I'm gonna get into too much this if I keep talking about this. But
I think in this particular case, though, where the person and a few of the other people who were talking in that thread were going was that what's the contribution of the brute force aspect of this? Like no programmer is going to sit down and try 1 million variations and see which one would work, right? Of course, like that's not even a fair comparison versus the generative component. Like is the advantage that we are seeing really the generative component or the brute force component? And is there a way to measure that? And should we even care? Right? So I think that's the interesting part of the conversation. Does it even matter? Like, okay, it is brute force, but who cares? It is producing code that is usable, right?
So shortcut learning is like a big phenomenon in all of machine learning, and I have been seeing it, in my NLP models that I work on as well. And I specifically know that the model is using these certain shortcuts, but in the end, as long as and it has no adverse side effects, I'm okay with that. And Yeah, so with respect to these specific competitive challenges, I think you can win them by gaming the system, and certain amounts of gaming is being done by even the contestants themselves. So I guess it's uh, yeah, it is unavoidable, I guess, for the model to pick up on certain cues that will help it win in certain tasks. So uh, yeah.
Yeah, and I think this discussion relates to a question that was asked by Moaz in the chat. So I'll just bring it up again. We've kind of touched on it, but Moaz is asking, do you think that AlphaCode has similar potential to AlphaZero, another DeepMind work, to eventually come up with creative solutions to these competitive problems? So again, sort of, I read this as, rather than applying the brute force method as fast as possible, also I wish I could do that myself, is AlphaCode actually reasoning and being creative? Or does it have the potential to?
I think so. I mean, I didn't have the opportunity to go through the code and see if it actually invented a new algorithm that never existed, rather than just working on certain primitives that are well known in the computer science field and also well represented in the training and the fine tuning data sets. But I think my experience with natural language processing models based not on source code but on just English text or multilingual text has shown that it's not just memorization. So there was a point when I was pretty skeptical. I knew, okay, this is pattern matching and everything. But then as the model sizes that I worked with increased, so I think the turning point for me was when I started working on a 3 billion parameter model, and when I saw uh, consistently how it was able to uh, you know basically I would yeah, I don't find a very good word, because common sense reasoning is like a loaded word. It has a lot of implications, but I don't find a better word to replace that. So I would use that. You can't say that it's doing anything else apart from that. When I look at some of the outputs that it generates on the prompting context, I think that was when I became like a believer. I had like a religious experience while working with the 3 billion parameter model, and ever since I then worked on a 6.5 billion one, on a 11 billion one, and on a 20 billion one, and every time I see the actual improvement when you and the scaling laws, they are true. They're really it is really true that adding more parameters, adding more layers is contributing to more.
You're starting to sound like investors to me, Suhas. You only care about billion numbers now. We only have a few minutes left, so I'm going to hear the verdict from each of you very briefly. Where are we? What's the most interesting thing about AlphaCode for you? And what are you excited to see next? And I think AlphaCode 0 is probably the next paper they're going to publish. So they're not going to publish everything in one paper, obviously. So maybe we can do S on Suhas and then Serena, and then we wrap up.
Sure. And I think kind of people are very familiar with my stance right now, and we don't have any biases. If we're proven otherwise, so be it. Well, we're going to be a believer in the thing that's closer to truth. But I want to point out a couple of things. One, and it does kind of it is derived from what we just discussed. Remember that these neural networks are not an accurate depiction of human brain. There is so much, for example, human brains, and there are spiking neurons. Human brains have spikes. These neural nets don't even have, at least the mainstream neural network, artificial neural network architectures don't have that. But the fact that it can produce similar behavior to humans, which we can believe it is to a great extent, as a function of the sheer parameter size, or a lot of other smart things that we've done during the past decades, is just mind blowing. So that's just amazing. So I take it. That's one. Another one, regarding creativity, just want to point out very quickly, the paper. So a lot of these computer programming tasks are supposed to be unseen and unknown. So if they're known problems, then there isn't much, even for humans, there isn't much credit perhaps. It's just to a great extent, memorization and creativity. It becomes to some extent it becomes a little bit of thin line. At what point the doctor is creative, at one point are they actually just applying what they know. But getting the philosophical aspects aside and putting that aside, I think it just does very similar to humans, given what I just mentioned. So I'm just excited to see what comes next. Specifically, I'm interested to see what prompt tuning helps us do these things, and what we can. I see that because that's, I think, one way that we can, as an ordinary researcher, by ordinary I don't mean not excellent. Everyone's excellent. But the tool set, not being pre-exposed to this massive and expensive tool set, we can do, I think, much, and there is so much room for this to grow and to do much more that it can do.
Very exciting space to look at. Definitely. Suhas, your brief verdict.
Yeah, so I would just like to stress on the kind of impracticality of a lot of what's happening here. So just to give an example, for example, the 11 billion language model that I was talking about, to use that in CPU, you need 90 gigabytes of CPU memory. To use it in GPU, you need 41 GBs. This is for inference. And inference on, if you use something like a Colab, for even a 3 gigabyte model takes 5 seconds for one example. So it's increasingly getting out of reach, and you can do things like model distillation, but then you also see a huge performance drop. I think even with AlphaCode, you have to see that they sampled 1 million samples for every answer, and sampling each example, each output would take several seconds on a person's machine. So imagine to solve one programming competition, if you have to sample 1,000 of them and then do the clustering and everything else, it's really computationally intensive. I think we are going to require a lot of magical inventions from our friends in the semiconductor space, the NVIDIA's, etc., to help us get anywhere close to achieving things at a practical level.
Or hopefully the compressions Ehsan was talking about will happen in a magical way, and we get better results. Serena, what are your thoughts?
Yeah, kind of similar to what Suhas was saying. I think it's fascinating that the tasks that AlphaCode has been able to achieve, especially because AlphaCode, in my mind, is just based off of transformers, which I think came out in 2017. And it feels like for the past few years, we've been making incremental improvements to the architecture and also moving towards engineering and compute costs that, as Suhas said, are inaccessible. So I'm curious on two ends to see how we continue leveraging transformers, but also I'm curious to see if any researchers come out with something substantially different. And we also I thought we had a question in the chat. Amir, what are your takeaways?
I mean, this is definitely very interesting, and I'm sure they have observed more than what they have published so far. So I'm curious to see what comes next, as they have done previously. Like AlphaGo, AlphaZero, etc. So they do have the support of Google, which is a lot of compute and data. So it's amazing to watch what they're up to and what they're doing. Definitely, a lot of interesting questions around applicability of things like this in real world. But it's a step forward, and I'm excited to see where it goes. Come back next week. We're going to talk about ethics, machine learning, and product design. A very interesting topic related to a letter we wrote to Toronto police recently as well. But many other topics that we're going to talk about. Make sure you subscribe to our channel and come back every week to see more. Thank you so much, Suhas, Ehsan, and Serena for today. I learned a lot, and hopefully this was sufficiently random for you as well. Thank you so much. See you next time.
Pleasure to be with you.
Bye.
Bye.